Okay, we can start. Okay, good morning, everybody. We've got an ideal weather for the conference. I haven't seen this room so much crowded yet. And thanks to Neven, you ordered it very well. I do appreciate everybody who came. And it's my honor and great pleasure to introduce the plenary speaker. Professor Robin Smith has been one of the key persons at Center for Process Integration and the director for many years at UMIST and later the University of Manchester. He has authored numerous papers, but some of them are the most highly cited papers in the UK and ever. He is also Fellow of Royal Academy, which is the UK equivalent of Academy of Sciences. He is the Fellow of IChemE, and recently he was awarded by Roger Sargent Award. Roger Sargent was the founder of Process System Engineering, the professor at Imperial College, and in his memory, every year the top persons around the world are awarded by this medal. So, Robin, the floor is yours, and you've got enough time to tell us what are the new developments.
Okay, thank you. Everybody hear me okay? I think so. Thank you all for coming. Yeah, as Yuri says, no doubt nothing to do with the thunderstorm outside. It's all to do with your interest in rethinking future industrial energy systems. I'm going to take a broader perspective as well, not just look at industrial systems, but try to look forward to how this has an impact on society. But let's start by looking at industrial energy consumption and emissions. Now, unfortunately, I can only point at one screen. You've got the luxury of being able to look at two, but I can only point at one. So I'm going to point at this one. I hope that's okay with everybody. Well, let's look at the industrial sector. If we break down the emissions from the whole of society, then it breaks down as we see here. Can't see it too clearly, but the biggest bar there is one for electricity and heat generation. But when we take that and we put it inside of the industry, which it is being the places where it is actually being used in industry, then it turns out that the industrial sector turns out to be the largest emitter of CO2 emissions, and individually it accounts for some 36% of the global greenhouse gas emissions. 2/3 of that comes from a small number of industries, and you can easily guess it's industries like steel, cement, chemicals, petrochemicals. In the UK, we have made a commitment to decarbonize, and we have committed to create the first net zero carbon industrial cluster by 2040, and at least one low carbon cluster by 2030. So that gives us a picture that the industrial emissions are key if we're going to solve this problem of having a sustainable future. So industry is the largest consumer of energy worldwide. You see here the breakdown, and some 32% coming from industry. What's interesting also is that you see that a large part of this, most of it, is actually down to process heating. Some of it is electricity generation, that's significant, but the process heating is a major element there. So 69% of industrial emissions are from the process industries of that industrial sector, and that accounts for about 2/3 of industrial emissions. So if we just pursue this issue of how that energy is used, it's shown here as a breakdown in terms of process heating. So we're taking this part of the energy consumption here, 60%, and showing it here as it's broken down in terms of its the temperatures at which it occurs. And although you can't read that, I can tell you that what it's actually telling us is that around 50% is relatively low temperature heating. Of course, if you go to steel making, it's very high temperature, but most of this heating goes on below 500 degrees C. And that's key to us. Most of that would be supplied via steam, but we have different media coming into play. We've got fired heat, furnaces, we've got steam, we've got hot water, all coming into play. Now, if we look at the trend with energy consumption, then we see here that there's a steady growth in demand for energy in industry through time, and around 2014 here, we saw a decrease in the rate of increase. I choose my words carefully here. That we're not seeing any decrease in consumption. The rate of increase is coming down a little bit. Well, it's coming down significantly. Slowed down to 1/3, that rate of increase. And that's good news. It's remarkable. But if we just project going forward, what the implications of that are, we just trend that away into the future. That means we're going to use 30% more energy before 2040. Now, what does that mean in practical terms? It means adding another China and another India onto the consumption of energy, and that doesn't appear to be too sustainable. So, alone, energy conservation is not going to solve the problem. We've got to reduce our demand for fossil fuels and their associated environmental impact. So, challenges here are we want to switch to renewables. We also want to carry on with energy efficiency. Both of them have a key role to play. And what we're looking for in the long term is a 90% reduction in the CO2 emissions by 2050, and that's so that we can fulfill the Paris Agreement and keep our global temperature rise below 2 degrees C. That's the goal, and that trend is then to move us to a more sustainable use of energy. Let's look then, if renewable energy is going to be a key player, let's look at the growth and how that's going. If we start at the current level, we start here with a baseline of 2015 and look at how renewable energy is growing. It starts at 2015 with some 19% of global energy demand coming from renewables. In power generation, that means 23%, but in the industrial sector, only 9%. So the industrial sector is lagging behind in terms of its adoption of renewable sources. And then we project that through to 2030. That takes us to somewhere in the region of 21 to 37% of the global energy demand being satisfied by renewables, which in industry would be projected to be 13 to 23%. Now those are rather large bands. The lower bound here is simply by carrying on with current policies. If we carry on the way we are doing, then we're going to achieve 21% and 13%. If we accelerate the implementation of renewables, then we can bring forward much better prospects, 37% and 23%. So it depends very much on policies as to how successful we will be. So project it forward then to 2050, and we see some 23 to 61% of global demand being satisfied by renewables. In power generation, higher, as we would expect, 37 to 82%, and in industry, lagging behind 16 to 39%. So the industrial sector certainly is lagging behind, and the good news is we're looking to something like 3 times the amount of renewable energy being used. So that would give us effective decarbonisation, but it also brings problems with it. It causes fluctuations in supply, wind and solar. We don't have to explain why we get those variations. And to compensate for that, we need additional electric generation capacity. So let's follow that through now and look at the implications in a bit more detail on future industrial energy systems. We've got to start by core generation. Combined heat and power generation, we use the energy both to generate electricity, and the energy that we're not using is used to generate heat, rather than the standalone arrangement where we have standalone power generation and we fire fuel to provide the heat that we need separately. There's no new concept there. The Victorian engineers were very good at implementing this. It was well known to the Victorian engineers, but we still somehow keep on learning this lesson, that combined heat and power generation is the most efficient way to generate electricity and heat. And if we use CHP, some 40% better in terms of the efficiency. But what we need to do then is to look forward and see how we might exploit that further. And let's start by where we are now at the moment. What we would tend to do is we have electricity which is here being distributed from a substation. The electricity is coming from centralized power generation via a centralized grid, but we'll expect to see certainly more solar and wind contribution to that supply, which would then go off to the residential consumers, to the commercial, industrial consumers here. And we're likely to see also conventional combined heat and power here. Not too much of it, but certainly some there. Supplying heat and electricity locally to commerce and industry. And what we need to do is to make this whole concept more flexible and bring in industry into this picture. So here we've got industry, the heavy industry, playing its part in society, but being supplied here by another CHP system, combined heat and power system, which is linked up to residents, perhaps providing hot water via district heating, electricity going into the substation here, electricity may be going directly into industry, waste heat from the industrial usage here being used usefully in this flexible CHP plant, probably being upgraded to make it something useful. So what we're looking then towards is a more distributed nature of power generation. Distributed, we obviously need to interact with the grid, we can provide both thermal energy and electricity with this arrangement, and we can also produce electricity for the grid. So these flexible CHP systems can provide grid services, and I'm sure are going to be important in the future, but there's very little attention being paid to them so far. Very difficult to find examples even of this kind of centralized combined heat and power arrangement. Let's look in particular now at a bit more detail of an industrial system. And we're supplying heat here in an industrial system. So a few words of explanation for those who are not familiar with steam systems. We use steam for most of the heating in our low temperature applications in industry. And how do we generate the steam? Well, we fire fuel in a boiler, generate steam. Here it goes into a steam header, which is distributed to the various users. This is high pressure steam, and then this is going to be at a high temperature, and then we let the pressure down to lower pressures of steam, medium pressure and low pressure steam. We let it down through steam turbines, and this is a good example of industry using combined heat and power. We generate the power and we take the heat and use it for process heating. So we see here process heating at the high pressure, medium and low pressure levels. We also got, just to complete the picture, some letdown stations, and these are controlled arrangements to control the pressures of the steam headers. But we are traditionally feeding into this steam system by firing fuel in a boiler, generates steam, goes in here. Now that's a typical arrangement. If we go to what's likely to happen in the future, we're likely to see more renewables coming in. Now, renewable energy is going to come mostly in the form of electricity. So whether it be hydro, whether it be solar, whether it be wind, we're going to get our form of energy and electricity, or much more of it as electricity, in which case, rather than having a fuel-fired boiler here, we're going to have electric boilers. So just like a big immersion heater generating steam. This has important implications, because if we were just to take in electricity rather than firing fuel, then we would use our electric boiler to generate steam. But there would be no point in having steam turbines, because there would be no point in turning electricity into steam and then turning steam back into electricity. So the system will have to change completely if we adopt this kind of renewable energy source. But of course, life is never quite that straightforward, because we have other sources of energy which are likely to come in as well. For example, biomass. We can bring in biomass as a source of energy, whether it's crops, agricultural waste, whatever it happens to be, and it comes in as some form of energy here, which is likely then to be fired. And we're going to have in industry a lot of waste gases. Certainly in the chemical industry, you can't get away from the fact that we produce waste gases. The waste gases can't just be discharged to the atmosphere, so you burn them. You may as well burn them to produce electricity, produce heat and electricity. So we've also got the possibility of introducing waste to energy in this. So take domestic, commercial waste and transform that into energy. And so we've got a mix of different sources. We're likely to see more electric boilers, but we probably can't get away with removing all of these fuel-fired boilers, even if we are only firing in them biomass and waste gases. So we've got the possibility of a completely different system, configuration, and operation. And what we want to know is what's the most appropriate mix of sources and technologies. Another feature, particularly as we introduce more renewables, is that we have problems with security of supply, variation in supply, and we need to think in terms of integration of storage, electricity and thermal storage. So electrical storage, I think probably the three prime ones I would think of were pumped hydro, but pumped hydro, you need to be in a place where you can pump water up to a hill in large quantities and leave it there until you need it and run it down the hill. Liquid air storage systems, where we, when electricity is cheap, we liquefy air, we store it as a liquid, and then when we need power, we allow the liquid air to vaporize and expand through a turbine to generate power. There is quite a large pilot scale facility in the UK demonstrating this as a viable option. Most of the talk, though, is about batteries. A lot of talk about batteries, particularly grid storage of electricity. But we also have the possibility of storing heat. We can do it in our industrial steam systems using steam accumulators. Again, this is nothing new. The Victorian engineers were very good at using steam accumulators. We can also store as hot water, even though this is a less efficient way to store heat. So we want to know what type, what size, and we want to know then how we are going to transition this whole thing from where we are to where we want to be in the long term, integrating the renewables, the different forms, different sources of energy, along with grid electricity. We've got storage, and how do we link everything up and make sure that everything is supplied securely? We need to know the configuration. We need to know, another important point is whether we are going to centralize or distribute the power generation, and maybe use a combination of the two. So, where does it get to? It gets to our goal here. Our goal here is to develop a system, a design and optimization framework that takes in the needs of the industry, so heating and cooling profiles, the power requirements, and that design and optimization framework, which we want to develop, will design the utility system, the energy system, whether it be distributed or centralized, and also tell us how to operate this system, the operating strategy. Into this, as options, we will have fossil and renewable energy sources, a full range of energy conservation technologies, storage of steam and hot water, and also power storage. And then we have constraints that we're going to have to live with, constraints on the utility options. We're going to have time dependency coming in here as well, because we can't generate solar power at night. We've got life cycle costs which need to come in, and we also want to put in sustainability constraints. And if we can develop this framework, then what we can do is we can use it to develop roadmaps to evolve from where we are to where we want to be in the long term. We're not going to get there in a single step. So we have to evolve over a period of time and develop roadmaps to see where we want to be in the long term. So how do we do this in a bit more detail? How do we do the conceptual design of future industrial energy systems? Well, a little bit of detail. I can't go into too much detail. I know there's a mixed audience here, but I'll try and give you a flavor for how we're going to do that. Well, we start with, on a site or in an industrial cluster, we have processes that have energy demands. And we look at it in terms of temperature on this scale and energy enthalpy on this scale, heat on this scale. And we've got different processes. What we do is we combine them together in that cluster into two profiles. This profile here on the left shows that we need to reject heat, so we've got waste heat. We want to do something useful with it. here we've got our heating demand. So heat's coming in here somehow to satisfy all of these requirements. This is a combined curve from these curves up here, and this is a combined cooling requirement from these individual cooling requirements up there. So how do we do it? Well, in this intermediate temperature range here, we can use steam. We can cool with steam by generating steam, or we can use steam to provide heating. So steam serves two purposes here. We want to know the number of steam mains, the operating conditions of those steam mains. For the production of the steam, we want to know the type of equipment, the fuel that we're firing, the size, the load. At the higher temperature end here, too high to provide with steam, then we're going to have to provide some fired heating, a furnace. Down here at the bottom end, we've got cooling, too cool to involve with the steam system. So are we going to use cooling water? Are we going to try and recover it with an organic Rankine cycle? Or are we just going to capture it as hot water and use it usefully somewhere else? So what are the degrees of freedom? Here is a steam system like the one I explained before. Boilers, a gas turbine here with a heat recovery steam generator. Here's steam generators producing steam from waste heat from the processes, steam turbines letting down between the steam mains, deaerators producing the boiler feed water. And for the boilers, we want to know what type. Are we going to use electric boilers, biomass, waste heat boilers? What type of fuel, biofuels, natural gas, waste gases? What temperature and pressure we're going to have, what size and load we're going to have. And then we have another complication. Another complication is that this is not going to operate at steady conditions. It's going to vary in its operating conditions, and the performance of this equipment in terms of its efficiency will vary according to its load. So its efficiency will vary, and we need to take that into account. So the models need to capture the effect of load on efficiency. So here then we've got the steam turbines, similar kind of story. We need to know the type, the size, the inlet and outlet conditions, and the efficiency of that turbine will vary according to the load that we put on it. Gas turbines, similar story. We want to know what type and size and so on, what fuel we're going to use, but the efficiency also varies with load. So we also want to build in flexibility in terms of the number and sizes of the units. Now here is an additional complication which is often being neglected in the design of these systems. They're never at steady state conditions, but they always must operate. Otherwise it creates major problems and even safety problems in the processes, in the manufacturing processes. So we either use large units at part load, operating most of the time, which we term active redundancy, spare capacity, or we use small units at full load, one switched off, which we term passive redundancy. And we've got to make basic decisions here. This utility system, this energy system, must always operate. Even though it's got a varying demand on it, it's got a varying supply to it, it still must always operate. So we can use bigger size units, which might be more efficient, but when they go to partial load, they become less efficient. Fewer units might be less expensive, but with fewer units, it becomes less reliable. So we have some basic decisions to make. Here's a steam system, and maybe we want to put in some redundancy here, some spare equipment, an extra boiler just for contingency, and an extra steam turbine there. And these are basic decisions that we need to make. And so for those types of units, more units of the same type or more units of different types but performing the same functions, also a possibility. So here, rather than having a steam turbine, we have here a gas turbine with a heat recovery steam generator. So multiple design and operational degrees of freedom, and these variables are highly interrelated. So it's a complex optimization problem. So for the steam mains, we need to know whether we've got the right number and size. Here's the range over which the steam mains are going to operate, and maybe we decide we're going to have 2 steam mains like this operating somewhere in these ranges, and we don't quite know where yet, but we're going to decide that later. And for the high temperature, we're going to use a hot oil to heat it, and maybe we're going to introduce a 3rd steam main. So if we introduce a 3rd steam main, like high pressure steam as we've done here, this may bring us benefits. So we need to know the steam mains pressures, and we need to know what kind of conditions under which they're operating. So here we see over here on the right a site cooling profile where we're generating high pressure, medium pressure, low pressure steam and rejecting heat to cooling water. And over here we're using high pressure, medium pressure and low pressure steam. And there's a fundamental assumption there that the only heating from the steam and the only cooling from the steam is all at saturated conditions. Now that's just to simplify the diagram for the moment. I'll come back to that point. So maybe we choose to use medium pressure steam at a different pressure, so we drop the pressure. And that might allow us to generate more power in the steam turbines. But if I'm going to drop the pressure here, I'm also going to have to drop the pressure over there on the using side, which means that I'm going to have to use more high pressure steam and less medium pressure steam, which means I'm going to lose power generation capacity. So it's not a simple trade-off, this. Another point that we need to bring in is that steam is generated in the first instance by taking boiler feed water, preheating it, evaporating it, and then superheating it. And the synthesis methods which have been published to date use only the latent heat part of the steam. But we must include the boiler feed water preheating and the superheating. This is an essential feature. Just to give you an idea of the kind of errors which this brings in if you assume only the latent heat. High pressure steam, the latent heat is about half of the total energy to take you from boiler feed water to superheated steam conditions. So major errors if you don't include these effects, and you might think, well, this is a fairly trivial addition. It becomes very non-trivial when you start to do the calculations. And when we're doing accounting for the use of the steam here, the processes are using steam for their heating. They might want to do desuperheating of the steam because they don't want superheated steam, and they might want to do flash steam recovery. Another complication is that we have non-isothermal mixing in these arrangements, which creates mathematical problems for us. And so how do we solve the problem? Well, we're going to get the structure that we want by creating a superstructure. I'm sure a lot of you're familiar with the concept, but basically what you do is you create a structure that has all of the features that you might potentially want for an optimal answer. And you're not going to include them all in the final design, but what you're going to do is you're going to create this superstructure. You're then going to optimize that superstructure, and you're going to get the optimization to remove the structural features which are not economic. That's basically the approach that you're going to use. So you're going to optimize a superstructure, including all the structural options to obtain an energy efficient structure and the optimum conditions, the operating conditions for the steam headers and all the rest of it. So the problem formulation for design and determining the operating conditions, part of it is that we have a mixed integer program. We make our discrete decisions by introducing integer variables, 0, 1 variables, 0 if it's not there, 1 if it is there. And then we've got other parts of the problem which are nonlinear mathematically. So we have a nonlinear program. This accounts for things like equipment performances, steam thermodynamic properties, and then when we put the two together we have a non-convex mixed integer nonlinear program. The people who enjoy this kind of optimization work rub their hands when they see, with glee when they see an MINLP problem. I'm afraid I go yuck and accept it and then move on because it brings in all kinds of complexities in the solution. So it becomes a complex and time-consuming solution. Another problem. Previously, designs were based on nominal average operating conditions for each process. But in reality, things vary through time. If we take a yearly mean demand, that might lead to suboptimal solutions and inaccurate economic evaluation. If we account for the variable demand, the design is going to be much more resilient, but it's also going to be a much more complex problem to solve. So how do we solve this? Well, we introduce multiple periods. So we slice up time into periods, and within each period, we assume things are at steady state. So we've got lots of these different periods to account for the variation through time. And this might be simply relating to the season as we change through the year, and then within each of these periods, we might have seasonal periods, so we might want to take account of changes through the time of the day of the week, and the time of the year, the season of the year. All of these we might want to do. And how do we deal with that? Well, we've got to create a structure where it looks schematically like this, where we've got these different operating periods, and we've got this design which has got to function across these different operating periods, but it will function different ways in terms of its economics and its environmental impact as it goes through those different periods. So we need to synthesize the utility system, accounting for those energy demand variations. We also need to include energy storage. So for steam, we can put in steam accumulators, for example. This can give us short-term storage of heat as part of the system over here, but it's a relatively short period, hours or days at the most. We can bring in battery storage, different kinds of batteries, lithium ion, lead acid, and so on. These have different efficiencies, different costs, and also short-term storage, but this time possibly up to a week in terms of the storage. And we've adopted two different approaches to the optimization. We've tried different ways to solve the problem. Same problem, but different solution strategies. We tried using, for those who understand these systems, a successive mixed integer linear program. It works okay, but doesn't give a guarantee of the global optimality. It gives you answers, but not necessarily the global optimum answer. It's relatively fast. It runs in something like 500 seconds or so. But the approach that we've adopted in the end is a nonlinear approach where we use a relaxed mixed integer nonlinear programming approach followed by a nonlinear subproblem. This has been used previously, so we're not claiming any novelty in that. We have researched it, compared it not just with the kind of successive mixed integer linear approach. We've also compared it with the commercial solvers like Baron, if you're familiar with that, part of the Gamma suite. And we find it gives much more, the approach that we've developed, much more robust answers with a guaranteed optimality. And relative to the Baron software, it runs about 10 times faster. So we've got a method to solve our problem. Let's try it on a case study. So here is a site. It's a 6-plant chemical cluster. We want to know the utility system to satisfy the thermal and electrical demand. We've got electrical price fluctuations, which we'll see on the next slide. We've got semi-continuous processes, and we've got variation of the production profiles. We've also got maintenance and shutdown. So you see here the operating profiles. This one is fairly steady state. This one is up and down. This one is up and down. So we've got the operating profiles here for this chemical cluster, varying through time. The constraints we're going to impose are utility temperature constraints, equipment load and size, and we're going to restrict ourselves on the import and the export potential to 1 and 10 megawatts. We've got electricity price fluctuations across the day. We've got off-peak, peak, and base price. We've got across the year, we've got winter, summer, and mid-season. Some of the numbers are up there for you, but another point to note here are the emissions factors for CO2 emissions, for grid electricity, fuel gas, natural gas. We've got those emissions factors in there because we look at CO2 emissions later. The variation of the annual energy demand, it's been divided into 20 periods, each with 3 tariffs, giving us a total of 60 periods that we are going to analyze the problem for. We're going to also analyze 2 scenarios in order to analyze the effect of energy demand variation, and that's firstly to minimize the total annualized cost, and also then to just minimize the carbon dioxide emissions. Firstly, if we optimize for total annualized cost, then we will see here the solution for the energy system for that cluster if we assume simply the average conditions. So we're assuming average conditions here, nominal conditions, and that's the design that we get. Compare that then with the design that we get if we assume a variable demand. It looks superficially similar, and it is kind of similar, but what you see are different operating conditions and different design configurations as a result of taking account of the variations. And this shows the electrical operation to satisfy the electrical demand. So the thick line at the top is the electrical demand and how we are satisfying it. In some cases, you see here we are importing, and sometimes we are exporting electricity down here. So the electricity is here in this solution being satisfied by generating electricity from 4 steam turbines, with some export and some import in some cases. The thermal demand here, we see the thermal demand, this line here, varying through the year, and we're supplying that with a combination of 2 boilers and a hot oil circuit down here. We'll also note here why we are dipping down and importing electricity here. We're importing electricity at this point here because we don't have a high thermal demand there, and therefore we can't co-generate our electricity. And that's what's leading us to import electricity at that point there. So another point to note is, although we have included energy storage as an option, it's not picked it out. What this is doing is it's designing a flexible utility system, and it's paying for and operating a flexible utility system rather than using storage. So what happens if we push the sensitivity of the economics here? And this is a sensitivity analysis which shows what happens if we vary the difference between peak and off-peak electricity. And we've gone here from 40% where we are all the way through to 230% difference. And we've gone this far in order to demonstrate just how far you need to go before it becomes economic to bring in electricity storage. So it needs quite a big difference in the peak and off-peak electricity prices in order to make electricity storage economic. And these are lead batteries, and it requires 2.3 times higher peak price in order to make them economic. If we were to use spot market prices for the electricity, we're likely to see a different story again. You can analyze this problem either using well-defined tariffs or using the spot market. The spot market gives wilder variations, and it's likely to see more storage under those conditions. But doing the calculation again with minimizing CO2 emissions, we get a different picture. Here is the electricity, and there is the demand for electricity, as we see here. The picture is different now. We still got a lot of generation of steam from steam turbines, but you will see also here batteries being used, they're being charged down here and discharged up here. So battery storage is starting to kick in here in order to reduce the CO2 emissions. Thermal operation, pretty much as before, 2 boilers and a hot oil circuit. Overall, a reduced thermal load as a result of the optimization, but further analysis would be required here to get this trade-off between CO2 and total annual cost. So energy storage becomes economically attractive once we start to bring in decarbonisation objectives. This looks at the effect of the economics, and the one maybe shown here in red is important, as that we minimize for CO2 emissions. Surely, yes, it does bring down the CO2 emissions significantly, but it also pushes up the cost significantly. So, summarizing this study then, utility system design based on nominal consumptions can lead to lower capital cost, but lead to a lower efficiency and lower and higher greenhouse gas emissions. Based on current energy prices, it's cheaper to use the utility system components rather than to incorporate energy storage. So cheaper to incorporate flexibility into the design rather than to use energy storage. I'm a bit surprised by that. Maybe you are, but I'm a little bit surprised. But that's how it is. It is what it is. At significant fluctuations in electricity price, then storage can have the potential to reduce the total annual costs, but it really does require a significant difference between peak and off-peak electricity for that to happen. And storage has the potential to reduce CO2 emissions. However, there's a significant trade-off here between cost and the performance. I'd like to just finish off now by putting this within the context of energy and society. Industry at the moment pretty much operates on its own, separate from society in terms of energy. But in the future, we need to bring all of this together, energy and society. So here is society, including industry, transportation, commerce, domestic energy, aviation, all the rest of it. What do we need overall? We need electricity, we need heat, and we need transportation energy in order to satisfy the requirements of society. And these have traditionally not been integrated. Another problem that we need to understand is that energy is competing for resource with the supply of water and food. And traditionally, we haven't looked at this problem either. So this needs, the provision of energy needs to be considered within the context of this so-called energy, food, water nexus. So what is the nexus? Well, electricity generation consumes some 15% of the global freshwater withdrawals, so significant interaction there. 18% of the global energy is consumed for water extraction, treatment, and distribution. Food production accounts for 70% of the water withdrawals and 30% of the energy consumption. So therefore you see the basis of the energy, food, water nexus. And these interrelationships among the nexus are really critical to us going forward. So the security of the energy, water, food nexus is a central challenge to the goal of sustainable development. As far as energy is concerned, any sensible strategy has got to start with demand reduction, whether it's domestic, commercial, or industrial. So that's the place to start. The traditional energy supply chain has everything separate. We generate electricity quite inefficiently in standalone power stations. We then put it into a central grid where we have other losses. We generate the heat domestically by firing fuel in our homes. And industry over here on the right does use combined heat and power, but if you look at the way they use energy, around 40% for the large-scale energy users gets simply thrown away as waste heat. Rather than use the traditional model, we've got to use, I think, move towards a distributed system where we have here a distributed arrangement of energy generation linked up to the different sources of energy, waste heat from industry, sending heat off to local commerce and domestic requirements and so on, electricity providing transportation energy in the future, power storage and heat storage. So rather than centralize everything, let's distribute everything. Now, next thing is, there's no one-size-fits-all solution to this. So for a geographical region, there's no single solution to solve this problem. For example, if we take the example of a city centre community, that's going to have different requirements from a rural community. So a city centre, densely populated area, domestic waste as a possible source of energy, a rural community, sparsely populated with agricultural waste as a significant source of energy. The two don't marry together. So for a geographic region, we should divide the region into characteristic zones, exhaust the potential for demand reduction, and then apply solutions based on distributed energy systems. So how do we optimize the system integration? Well, we've got to look at the basics. Over here we've got primary energy, solar, wind, hydropower, biomass, and so on. Over here we've got society and industry needs. We need electricity, heating, cooling, energy for cars, energy for buses, and so on. And what we need to do is to link the two together as efficiently as possible. Different steps we need to go through for that. Primary energy conversion, use energy vectors to move the energy around. Secondary energy conversion before we can link these two together. So what are the options? Primary energy conversion, we've got wind turbines, hydro turbines, solar, and so on. The energy vectors, we can use electricity, hydrogen, ammonia, synthesis gas, lots of options here. We can use storage at that point of these energy vectors. We then need a secondary energy conversion, which could be, say, hydrogen going into fuel cells, electricity going into electric motors. We can also store energy at that point as well, storing electricity, storing heat, before we link up, finally, before we link up the primary energy with the needs. And of course, all this then has got to be constrained by the energy, water, food nexus. So the problem is there are an enormous number of ways to integrate the systems, but it's also an opportunity for novel solutions to provide novel ways to integrate different systems. So let's just finish up quickly with a case study, and this is from the UK. This is a geographic zone in the UK showing the thermal and electrical demand and divided into 39 bands across time. We look to supply the energy with a distributed energy center, lots of different options in there, gas engines, gas turbines, fuel cells, and so on. We've got variations of tariffs, and we've got grid emissions factors there, different prices going through time. And what we need to do is to model this system, and we did it using linear models in this case, and model the performance. The performance varied with load, but we linearized that. And for the optimization model, we discretized everything through time. We chose our different options using integer variables, as I explained before. We did part load, effects, CO2 emissions, and we formulated the whole thing as an MILP, a mixed integer linear program, constraining on the basis of maximum, minimum loads and maximum CO2 emissions. And depending upon the scenario you choose, you can get different solutions. So here we see the heating supplied with a complete import of electricity, no cogeneration, and we get a solution here based on heat pumps, boilers, and that's the solution where we don't allow power generation. If we then allow power generation and we make this an island solution, so this becomes self-satisfied, then we've got different kinds of machines generating power to satisfy the demand. We've got, you see there's a bit of a mismatch here, which is being satisfied by thermal storage. So we're using thermal storage, no power storage in this particular case. And another option is if we allow import-export of, creeping up on me here, I know lunch is waiting. And a different solution again, different combinations if we allow import-export. But the result overall was we applied this on behalf of the UK government to see what would happen if you use distributed energy to the CO2 emissions to replace the current system. Well, across the UK, and we did different zones across the UK, it's about 40% reduction in the CO2. But it's basically energy efficiency. It's not a significant introduction of renewables, no waste to energy, no power storage, and various things. Okay, finally, conclusions. Many potential sources of energy, each of which have their advantages and disadvantages. Variability of energy demand creates challenges for supply and the security of the energy, food, water nexus, a central challenge to the goal of sustainable development. Novel solutions can in principle be developed through optimization applied to the needs of geographic regions, and novel solutions need to be sought through novel ways to integrate energy systems. Finally, an acknowledgement to the guys who pay the bills, that in this case it was the Research Council of Norway. Thank you, and sorry for overrunning a little bit.
Thank you very much indeed. We just used the time, but I believe you will sacrifice a few minutes from the lunch. And we can maybe have one or two questions or comments. Yes, please.
Thank you very much for the nice and interesting presentation. Yesterday we had an optimized scenario for using of renewable energies as 100% by 2050. And in your concept or in your presentation, you illustrate that maximum is about 69%. What are the basic for your assumption? Yesterday we showed and we saw the assumption, but in your scenario, please say us what your basic assumption for this somewhat pessimist scenario. Thank you very much.
Okay, It depends whose report you read, whose projections you believe, and that's the basis of that. I think it was from memory, it was the International Energy Agency report that we took it from. But it depends whose report you read, basically, whose projection. It's a huge uncertainty. Whoever you read, there's a huge uncertainty in these numbers.
Okay, thank you. It's a few people dying from hunger, but the majority is still okay. Yes, please.
I was wondering, speaking of uncertainty, all of the analysis you showed is deterministic optimizations, right? Yeah. Using MLP and some linear relaxations. Yeah. Have you thought of introducing the vast amount of uncertainty in all of your analysis in some way in order to be able to communicate the results to stakeholders?
Fair question. To be honest, it's bad enough trying to include everything in a deterministic algorithm rather than putting everything then further into some kind of stochastic optimization, which is what you're asking for. And of course, as soon as I do that, I'll put some kind of distribution in there into the analysis, and everybody will say, where does that come from? But nevertheless, I think in principle you're right. You know, there's no certainty in any of this. There's always an uncertainty. But for the moment, we are trying to maintain that to be deterministic because it's bad enough as it is. And we still have quite a long way to go before we get all of the deterministic issues in there.
Okay, the last one.
Yeah.
I wanted to know that active redundancy, because part load operation, because in India part load operation in thermal power plant is not there. So, and the renewable energies are, you know, in the future is coming up. So how we can use this part load operations?
Use what? Sorry, I didn't catch the...
Part load operations. Active redundancy.
Oh, redundancy. Okay. You can be quite deterministic about the use of passive and active redundancy. There's certainly, you know, different ways you can approach this problem. We've very much in our case taken a kind of worst case scenario. What happens if one of the boilers breaks down? Can you still operate? That kind of approach. But we've also done research which allows you to put in reliability for this kind of equipment as well, and do much more of a rigorous reliability analysis. So you can take the active and passive redundancy in different ways. The way we did it, quite crude, I think, but nevertheless, it's a must to put in there to be realistic. But then, you know, because we are putting this together with a lot of other issues as well, we took a quite simplistic approach to how we account for it. But I understand your point now, and I think this is something that you can go into a lot more depth and detail in. We have done research in that area, but we've not included that kind of reliability theory into this analysis. Yeah.
Okay, thank you. Unfortunately, we should feed the rest. Robin is still up to Saturday, so you can discuss with him privately. And I've got a very nice beauty to present you the certificate.